Hello, my name is Stephen Christian, and today I'm going to be presenting about my Snapbot challenge results. So the first task that I did was the sideways walk, and the first thing that I did was I changed the sideways distance reward. So instead of rewarding X distance, it rewards Y distance, and I changed the lane keeping penalty from Y to X. And after doing that, the robot managed to walk sideways for a couple of seconds. However, it stopped midway. So what I did was I ch changed the episode length into 10 seconds, and it managed to walk even further. However, the problem was that um after a couple of seconds of walking sideways, it decided to just turn 45 degrees, 90 degrees, and then it walked normally. So what I did was I added this extra penalty here so that if the R heading is less than 0, then it multiplies the R heading by 100. And that managed to fix it. And the model walks around 3.5 units in the Y direction. And the position here is calculated from the torso distance. So this is the video. And as you can see, the problem with this is that it only uses two legs to move. So it definitely has more potential to be improved. And in fact, when I first trained it, the rewards just keep getting better. So this actually has not converged yet, and it can definitely be trained on more steps for it to converge better. And then onto the high jump. For this one, I chose to have a 7-second episode length. And the reasoning behind this one is because I thought that there will be more trade-off from um closing and reopening and reinitializing the simulation instead of just making the robot jump a couple of times. So I opted for a longer episode length where the robot can jump multiple times instead. So the first reward that I want to talk about here is the velocity reward, and this is a continuous reward, and this will be the first reward that incentivizes the robot to take off. So it rewards the Z velocity where it's upwards. So this means that the robot tries to gain as much Z velocity as possible. And when it has gained enough Z velocity, automatically it will also take off. And when it does, it will get rewarded by this takeoff reward here. Now, once it has taken off, it will be in an airborne state where it's going to be rewarded by this airborne reward for each step. And then when in the case that it ends, which is whenever it has reached the maximum amount of seconds, it will either get the terminal height here, which is a one-time thing, or it will get a rollover penalty, which is different from the default one. Instead of just doing -10 penalty, I chose to get the entire reward total reward and multiply by 0.75. So this is the result of the high jump. It jumps pretty well, and it got a highest jump of 0.3283, calculated from the highest torso Z position. If you saw the video earlier, it does jump on all four legs, which is good, and it's all synchronized. However, the biggest problem here is that it jumps before it fully lands. And what this means is that while it's going downwards, while the momentum is going downwards, it's already started jumping. So what this does is it reduces the max force throughput on the ground because it has to negate that negative momentum downwards instead of putting all the force to propelling itself upwards. And another problem is that most of the attempts that I've tried didn't converge to jumping on all four legs. Most of the time it will just alternate between jumping on two legs, which didn't give the robot that much height. So what I did to fix this was I added some exponential symmetrical reward for the position of the all four feet during liftoff. So what this did was basically incentivize the model to keep the height of all 4 feet approximately the same during liftoff. And this did do the trick. It did make the robot converge better. However, I haven't explored this idea fully yet. So my current model with this reward hasn't increased the 0.32 height yet. So I haven't fully explored that idea. And besides that, the terminal reward is also unclear whether it's useful or not. I tried removing the terminal reward. Sometimes it improves it, sometimes it doesn't improve it. So I think I have to do more experiment on that. And another thing is that it rollovers way too often, and that's presumably because the rollover penalty here is 0.75, where I should have probably lowered that a lot more, or even put that into negative. So the potential improvements that I thought that I could do was that instead of maybe relying on 7 seconds of the robot just jumping randomly, I could normalize the jump counts and then divide the rewards by 10. For example, I can make it so that the episode fully stops when the robot has jumped 10 times and then divide all the rewards by 10 to normalize it. And I can also initialize a bigger random exploration for the epsilon hyperparameter. And the hope for this is that it can converge into jumping on all four legs better. And of course, we can also add the symmetrical feet height. We can also add a reward for reducing the momentum when it lands. So when it lands, it should minimize the momentum as much as possible. And then I should also tune the terminal velocity reward and add more rollover penalty to prevent it from rolling over more often. And then onto the long jump. For the long jump, I realized that 7 seconds episode length was a bit bad because I didn't have the reward for the landing yet. So I decided to opt for a 2.5 seconds episode length, reduce the buffer size to 20 seconds so that it learns from it learns from newer episodes, newer buffers more, and I increased the step size to 3,000 because I reduced the episode length. So most of the rewards here are pretty much the same, except that I added this X velocity reward only when it's airborne. And what this does is it incentivizes the model to jump forwards whenever it's jumping. And then besides from that, I also added the distance rewards, which is the Euclidean distance of the X and Y of the torso coordinates um, while it's airborne. So when it lifted off and when it touched the ground, that's the distance reward. And then this is the video. As you can see, it didn't jump as nice as the previous task, but it did jump. It does jump a bit, and the results are that the Euclidean distance that's covered is 0.849, calculated from the torsos X and Y when the feet first took off and then when it landed. Now, the observation here is that it doesn't use all four legs. If you see here, one of its legs are not used. It's just stuck there. So it definitely could be improved. And another recurring theme is that it jumps before it fully repositions, so it still has to negate that backwards, sorry, that negative momentum going down. So sometimes it even jumps backwards accidentally. And then for the potential improvements, I also initially thought of doing curriculum learning. So I wanted to train it from the high jump task into the long jump task. And we can also add the reward for reducing the momentum. However, I didn't have enough time to implement the curriculum learning, so I had to stick with this model for now. And that's been it for my presentation. Thank you very much.